The ground beneath California is not calming down. It isn't resetting. It isn't waiting. It is moving again and again and again. Not through one massive earthquake. Not through a single catastrophic rupture that dominates headlines and then fades into memory. Instead, the shaking is fragmented, persistent, repeating. Sometimes minutes apart, sometimes hours. Sometimes stretching across days with no clear beginning and no obvious end. No mainshock, no aftershocks, just motion. This is an earthquake swarm, and it's still unfolding. What makes this moment unsettling isn't the strength of the earthquakes. Many are small, some are barely felt. What makes this important is the pattern, the repetition, the sense that California's crust is adjusting itself in slow motion, releasing stress in pieces rather than all at once. And when the Earth starts behaving this way, geologists pay very close attention, because earthquake swarms are not noise, they are signals. Most people think of earthquakes as sudden disasters. Pressure builds for decades, a fault snaps, the ground shakes violently, and then it's over. But that picture hides the truth. Earthquakes are not isolated events. They are moments within a process that never truly stops. A seismic swarm pulls the curtain back on that process. Unlike aftershocks, which follow a large earthquake as the crust settles, a swarm has no central trigger. There is no dominant rupture. No single quake explains the rest. Instead, stress is released through dozens, sometimes hundreds, of small slips clustered tightly in space and loosely in time. The Earth isn't snapping, it's negotiating. Right now, seismic networks across California are capturing that negotiation in extraordinary detail. Clusters of earthquakes are repeating along known fault systems. In some locations, tremors strike nearly the same patch of fault again and again, like a stuck record. In others, the activity migrates, creeping laterally or vertically through the crust as pressure shifts. Each earthquake slightly alters the stress field around it. That change nudges nearby faults closer to slipping, or temporarily stabilizes them. One movement reshapes the next. This is not coincidence. It's interaction. California's crust is not a single fracture waiting to break. It's a dense web of faults of different sizes, depths, and personalities. Some faults are locked tightly, accumulating stress for decades or centuries. Others creep slowly, slipping almost silently. Some switch between these behaviors depending on conditions. Earthquake swarms tend to form where these different fault behaviors collide. Imagine two fault segments side by side. One is locked, the other is creeping. As tectonic forces push the plates past each other, stress builds unevenly. The creeping fault slips a little, transferring stress to the locked one. The locked one resists, until it can't, and releases a small amount of energy. That release then shifts stress back again. The result is not one earthquake, but many. This feedback loop can persist for days, weeks, or even months. Stress isn't being eliminated, it's being redistributed. Depth plays a crucial role in this behavior. Many earthquakes and swarms occur in transitional zones, deeper than typical surface quakes but shallower than fully ductile layers. In this zone, rock behavior is complex. It isn't purely brittle, but it isn't flowing smoothly either. Here, faults are prone to repeated slipping rather than clean rupture. Another hidden driver of swarms is fluid pressure. Deep underground, water exists not as rivers or lakes, but trapped in microscopic pores within rock. Under immense pressure, that water can reduce friction along fault surfaces. When fluid pressure increases, faults that were once locked can begin to slip repeatedly. As fluids migrate, seismic activity often follows. This is why some swarms appear to move through the crust over time. The earthquakes aren't chasing each other. They're responding to shifting pressure conditions that can't be seen from the surface. California's tectonic setting amplifies all of this. The boundary between the Pacific and North American plates is not a single fault line. It's a broad zone of deformation stretching across the state. The San Andreas fault system splinters into dozens of major faults and hundreds of smaller ones. Stress moves through this system like electricity through a grid. When one segment adjusts, others feel it. This brings us to the question that dominates every conversation whenever the ground starts shaking. Does this swarm mean a bigger earthquake is coming? The honest answer is uncomfortable. Most earthquake swarms do not directly lead to major earthquakes. Many fade away as stress is gradually released. In some cases, they may even reduce the immediate risk on the fault segment where they occur. But swarms do not remove tectonic stress. They move it. And where that stress ends up matters. A swarm can increase pressure on nearby locked faults, subtly changing their likelihood of rupture. These changes are usually small, but they are measurable. They don't allow scientists to predict earthquakes. but they reshape probability landscapes. This is why researchers monitor swarms so intensely. Not because they signal doom, but because they reveal how the system is evolving in real time. Each earthquake adds data, depth, orientation, timing, magnitude. Together, they form a map of stress migration that cannot be observed any other way. This information feeds into hazard models that help planners understand which faults are loading, which are relaxing, and which are behaving unpredictably. Swarms also challenge one of the most persistent myths about earthquakes: the idea of the big one as a single inevitable moment. In reality, tectonic stress is released in many ways, sometimes catastrophically, sometimes quietly, sometimes unevenly. The Earth does not operate on human narratives. It operates on physics, and physics doesn't care whether the motion feels dramatic or boring. For people living above these faults, repeated tremors can be deeply unsettling. The unpredictability erodes the sense of stability. Each quake feels like a question mark. Is this building towards something? Or is this the release itself? That uncertainty is real, but so is the science. California has always behaved this way. What's different now is our ability to observe it. Modern seismic networks detect earthquakes so small they would have gone unnoticed decades ago. What once felt like silence punctuated by disaster is now revealed as constant motion. The Earth was never quiet. We just couldn't hear it. Right now, the swarm continues. Sensors keep recording. Scientists keep analyzing. Stress keeps shifting. The story is still being written with every new tremor. This doesn't mean California is becoming more dangerous. It means California is revealing what it has always been: a dynamic boundary between moving plates where energy is never truly at rest. The ground beneath your feet may feel solid, but beneath that surface, forces measured in millions of years are still at work. Faults are adjusting, pressure is migrating, and every small earthquake is a reminder that stability is temporary. California's earthquake swarm is not a warning siren. It's a status update, a glimpse into how the crust actually behaves. Not in moments of catastrophe, but in the long, restless process between them. And as long as the plates keep moving, the tremors will too.